This is our first video for Chapter 5. You're going to see a lot of review and a couple new ideas. But a lot of the things that you have looked at in the earlier chapters, you will see again, and you will know why you looked at them in the earlier chapters. What Chapter 5 helps us look at is forces and interactions. We've been talking about forces since day one, and now we're going to talk about how the forces interact. And this comes together in Newton's third law of motion. And we will practice a whole lot more with vectors. And if you didn't understand them before, we're going to keep practicing with them, and they're going to make more sense to you. This chapter also ends the first of our unit, the first 5 chapters, so we will summarize what we have been doing since the beginning of the school year. So this particular video is forces and interactions. Here you are, here's your friend, standing and leaning up against the wall. What are the forces? What are the interactions? Well, we've already been doing this, drawing force diagrams, and we know that he is pushing against a wall like so. And just out of practice, we have been putting a support force against our force diagrams. The logic now is that, in fact, that support force is real. The wall does push back in an equal and opposite way that our friend is leaning against it. We call this an interaction. It's really important. We're not talking about gravity. We're not talking about his feet in the floor. When we are looking at our free body diagrams, we need to be looking very specifically at an interaction and not taking into account the other interactions. An interaction is always between two things, two unattached, two separate things. And an interaction is always going to be a pair of forces. All right? So the hand is interacting with the wall, and the wall is interacting with the hand. If this doesn't make sense to you, imagine that instead of leaning against the wall, you and a friend are leaning against each other. When it is two people, do you in fact see that your friend is pushing back against you? There's a push this way, a push this way. And if you're at equilibrium, the summation of the forces is equal to 0. They are equal and they are opposite, the forces are. Let's look at another example, and this might make a little bit more sense to you. We've got a heavy-duty boxer here who has a mammoth force due to the muscles in his arm. And when he strikes the punching bag, it is massive. Are our forces equal and opposite? They are not, because there's some movement, so there's a little bit of acceleration. There's force here causing acceleration. Acceleration is equal to the force divided by the mass. In this case, it is the force. It is the force of his arm divided by a really, really big mass of the punching bag. So we get a little bit of acceleration. We get a little bit of acceleration, a little bit of change in motion. All right? What if our muscle man uses the same amount of force against something with very little mass? What is the, and again, our acceleration that we've learned from Newton's second law is the force divided by the mass. In this case, we have the same level of force times a tiny, tiny mass. So the acceleration is large. There's a whole lot of unbalance, and there's a whole lot of movement happening. The third example that the book gives you is a sledgehammer pounding in a nail or a spike. All right, it's very easy to visualize the direction and the magnitude of the hammer because we've swung that and exerted a great force downward. It might be new to you to think about the nail exerting a force back, but in fact it exerts enough force back to stop the motion of the hammer. Also, if you've ever done this, with your hand holding the hammer, you can feel that reaction. You can feel that force bringing. Sometimes it hurts your hand to hammer something really strong, and you can feel that coming up the handle. All right, that is a summary of Newton's third law of motion. The thing to think about is that forces, and we've been talking the same forces we've always been talking about. Always come in pairs in equal and opposite reactions.